Hello, everyone, and welcome to the next lecture on Taylor series. Um, so let's dive right in. Some announcements. Make sure you're working on everything in MyOpenMath. You will have someone available on certain days for you to come in and take quizzes in the mornings during our regularly scheduled class time. And then I will also provide you with times that you can go to office hours for other professors that are available for you to ask questions about Calc 2. Um, and that's that. So make sure you're working on stuff in MyOpenMath. Tons of stuff for you to be doing in there. So let's remind ourselves of Taylor series from last time. So suppose f of x is a function that has as many derivatives at the point a that we want. Then the Taylor series for f centered at a is given by the sum from 0 to infinity of the nth derivative of f at a over n factorial times x minus a to the n. Now notice technically what I'm not writing, technically I haven't written f of x equals this. For most functions, it will be the case that f of x equals this thing on the interval of convergence. There are some weird, nasty functions where that's not true. Well, where you only get convergence at a. For most functions, this is equal to the function for which you're finding the Taylor series. Okay. And if a equals 0, we call the series the Maclaurin series for f. Okay. So last time we found Taylor series and Maclaurin series. Actually, we only found Maclaurin series. Last time we found Maclaurin series for the function sine of x and cosine of x and e to the x and e to the minus x squared. Um, let's find a Taylor series now for the function natural log of x centered at a equals 1. I'll give you a second to pause the video and try this out on your own. And then once you think you have an answer, don't forget to find the radius of convergence and the interval of convergence. Play the video and make sure you got what I get in the next couple minutes. Okay. So the way to approach this problem, actually, there's a couple of different ways you can approach this problem. There is a way to do this from geometric series stuff that we've talked about before, but we want to do this using the Taylor series idea. So we're going to write the Taylor series, the sum n equals 0 to infinity of the nth derivative of f at a. A is 1 here over n factorial times x minus 1 to the n. Okay, so I need to start taking derivatives of f of x as natural log of x and plugging in 1 until I see a pattern. That's the general idea of how you approach these problems for a new Taylor series that you haven't seen before. So if f of x is natural log of x, then that means f of 1 is natural log of 1, which is 0. Okay. This also means f prime of x is 1 over x, which is the same thing as x to the minus 1, right? So f prime of 1 is 1. F double prime of x is minus x to the minus 2. So that means f double prime of 1 is minus 1. F triple prime of x is 2x to the minus 3. So f triple prime of 1 is 2. F the fourth derivative of f of x is minus 3 times 2, which is 6, times x to the minus 4. So fourth derivative of f at 1 is minus 3 times 2. And there you might say, oh, that's reminding me of minus 3 factorial. This one's 2 factorial. This one's minus 1 factorial. This one's 0 factorial. Seems like we're getting factorials here, but it's alternating. Let's look at the next one just to be sure. If it follows the pattern, we're going to get positive 4 factorial, right? So fifth derivative of f of x is minus times minus is plus, so 4 times 3 times 2 times x to the minus 5. So hey, yes, it's true. The fifth derivative of f at 1 is positive 4 factorial. And at this point, it's okay to say, okay, the pattern is that the nth derivative of f at 1 is, well, we're kind of in there's kind of two things going on. The first derivative gave me 0 factorial. Second derivative gave me negative 1 factorial. Third derivative gave me 2 factorial. So it seems like for all of these, the number of derivatives shows up here, but minus 1, right? Second derivative, 1 factorial, or minus 1 factorial. Third derivative, 2 factorial. Fourth derivative, minus 3 factorial. So it looks like we're getting something like um, n minus 1 factorial. And then we have a minus 1 to the, well, is it to the n plus 1? We need to decide on that as well. So with the first derivative, I got something positive. Second derivative, negative. Third derivative, positive. So that looks like an n plus 1 to me. And always check your pattern once you have it written down. Plug in n equals 1, 2, 3, 4, just to make sure. Now notice this only holds for n greater than or equal to 1. But our function evaluated at 1 itself, sort of the 0th derivative, is 0. Okay, so the 0th derivative of 1 of f at 1 is 0. Okay, so let's write down our final answer here. The Taylor series centered at a equals 1 for natural log of x is given by the sum n equals 0 to infinity of, well, so actually when n is 0, we get 0. So I can actually get rid of that 0 there. And what we're actually looking at is the nth derivative of f at 1 over n factorial times x minus 1 to the n. But that is the sum n equals 1 to infinity of minus 1 to the n times n minus 1, sorry, n plus 1 times n minus 1 factorial over n factorial times x to the n, which is the sum n equals 1 to infinity of minus 1 to the n plus 1 times n minus 1 factorial over n times n minus 1 factorial beep, boop, times x to the n, which is the sum n equals 1 to infinity of minus 1 to the n plus 1 over n times x to the n. Nope, I left off my center. I'm sorry, everybody. X minus 1 to the n. Let me fix that really quick. There we go. Make sure to copy down what you wrote before. Okay. And there we go. We'll find the radius of convergence and the interval of convergence in a second. But let me go into Desmos here and show you that this looks like the natural log of x. So there's natural log of x. Here's the sum from 1 to, again, technically it should be infinity of minus 1 to the n plus 1 over n to times x to the, oops, x to the n. I did it again. Sorry, everybody. X minus 1 to the n. And there you go. You can see that this is converging to that natural log function. And you can also kind of see, not kind of, you can see the radius of convergence, right? You can see where the power series is diverging away from the curve over here close to x equals 2. So that kind of gives us an inkling that the radius of convergence is going to be 1. So let's go and verify that by using the ratio test. Add a page here, use the ratio test. So we want to look at the limit as n goes to infinity of the absolute value of the n plus first term, which looks like minus 1 to the n plus 2 times x to the n plus 1 over n plus 1 factorial. Nope, sorry, it's just over n plus 1. Because that's the n there. And then divide by the nth term, minus 1 to the n times x to the n over n. Sorry, n plus 1. So we get a lot of cancellation. That just leaves me with a 1 there. This is the limit as n goes to infinity of x to the n plus 1 over n plus 1 times n over x to the n. That cancels with most of those and leaves me with an x to the first. So this looks like limit as n goes to infinity of absolute value of x times n over n plus 1, which I can drop the absolute values because n is positive. I can pull that absolute value of x out and evaluate this limit. That limit is just 1, and so this gives me absolute value of x. And the ratio test says that, so we've taken the limit. The ratio test says that the series converges absolutely when the limit that we take there is less than 1. Oh my gosh, I did it again. I am so sorry, everybody. There should be x minus 1s here. Sorry, everyone. It's been a long day. But everything I did is still generally holds, except for an x minus 1 to the n plus 1, x minus 1 to the n. Again, my apologies there. So this should be an absolute value of x minus 1. There we go. And now I get the correct interval of convergence. So now that I've correctly done that, if you did that and then erased what you had, and because of I did something incorrectly, I apologize, but trust yourself. Okay, so now this is the correct work for the ratio test. And so the interval of convergence, the radius of convergence looks like 1, which we kind of guessed that from looking at the graph. And so now we just need to know what's happening at the endpoints. This tells me that the interval of convergence looks like, well, 1 minus 1 to 1 plus 1. So it's between 0 and 2, right? 1 minus 1 is 0, 1 plus 1 is 2. So I need to check what happens at x equals 0. So when I plug in x equals 0, what do I get? I get the sum n equals 1 to infinity of minus 1 to the n plus 1 times minus 1 to the n all over n. This is the sum n equals 1 to infinity of, well, I'm going to get minus 1 to the 2n plus 1. The 2n, that's like minus 1 squared to the n. That will cancel out, right, to give me a positive 1. Now I'll just be left with 1 negative 1 there over n. But this diverges. It's the harmonic series. Or you could also say p series with p less than or equal to 1. So that diverges, and we do not include 0 in the interval of convergence. And then we check x equals 2. When I plug in x equals 2 into this, I'm going to get minus 1 to the n plus 1 over n times just 1 to the n, right? Minus 1 to the n plus 1 over n times 1 to the n. But 1 to the n is just 1, so this looks like a sum from 1 to infinity of minus 1 to the n plus 1 over n. And this, take a second and think. That's right, it converges by the alternating series test. So we do include 2 there. Okay. That's the alternating series, the alternating harmonic series, and we already know that that converges to natural log of 2, and we know that because like literally just plug in if this equals natural log of x, then plug in x equals 2 on the left. It's the same thing as plugging in x equals 2 there, and you get the alternating harmonic series. So pretty cool. All right. So let's talk about Taylor polynomials and the remainder of Taylor polynomials. Taylor polynomials are just the partial sums associated with the Taylor series. Okay, so the partial sums associated with the Taylor series are called Taylor polynomials. I don't know why I have that word a there. Are called Taylor polynomials. Okay, so we have the following definition. If f has n derivatives at x equals a, then the nth Taylor polynomial for f at a, and really sometimes you see this called the nth degree or nth order. But it is literally just the nth partial sum, right? Is the sum from, I'm using n for the last term, so I'm going to change to k for my index. K equals 0 to, sorry, capital N of the kth derivative of f at a divided by k factorial times x minus a to the k, which looks like f of a plus f prime of a times x minus a. There's the tangent line, by the way, plus the second derivative of f at a divided by 2 factorial times x minus a squared. There's the tangent parabola to occur, plus so on, so on, so on, up to the nth derivative of f at a over n factorial times x minus a to the n. Okay. So there are my Taylor polynomials. They're again just the partial sums. So technically not new. You know about partial sums for series. We're just using that idea now for power series. Okay. And then once we know that, we also define the nth remainder as f of x minus Pn of x. Now, this is technically different than how we define remainders for just series, because here, f of x, well, where we have f of x, normally we would have the full series, right? And so the remainder, we're interested in how do the partial sums compare to the original function f, and not necessarily the Taylor series, which again, I'm being pedantic here, could be different things. They could look very different if the function is very weird. And um, I honestly, I probably won't show you a case where that happens because it's a bit technical. But if you want to see that case, email me and I'll show you. Okay, but that's how we define the nth remainder. Our n of x is just f of x minus the nth Taylor polynomial at x. All right, so if we've already found the Taylor polynomial, or sorry, Taylor series for a function, then we can write down the Taylor polynomials for that function just by chopping off the Taylor series. Okay, so everyone take a second, pause the video, and see if you can remember the Taylor series for f of x equals e to the x. And it's actually at a equals 0, so really the Maclaurin series. Hopefully you remember that that is the sum from 0, oopsies, n equals 0 to infinity of x to the n over n factorial. There is the Maclaurin series for e to the x. Okay, pretty cool stuff. So how do we use this to write down the Taylor polynomials centered at 0? Well, I just chop these off at the corresponding terms. So P0 of x is literally the sum n equals 0 to 0 of x to the n over n factorial. It's literally just the first term in the Maclaurin series, which is 1. The remainder, r 0 of x is e to the x minus p0 of x, excuse me, e to the x minus 1. Okay. Take a second and write down what you think p1 of x is, and p2 of x, and p3 of x, and also write down the corresponding remainders. Okay. Hopefully you paused the video and tried this out. This is the sum n equals 0 to 1 of x to the n over n factorial, which gives me 1 plus x to the first over 1 factorial. That's just 1 plus x. The remainder is e to the x minus that. And if you want to simplify that, that's e to the x minus 1 minus x. Second degree Taylor polynomial centered at 0 looks like this. And so this second remainder looks like e to the x minus 1 minus x squared over 2 factorial, which is 2. And the third degree Taylor polynomial centered at 0 looks like this. 1 plus x squared over 2 plus x cubed over 3 factorial, which is 6. And so R3 of x equals e to the x minus 1 minus x squared over 2 minus x cubed over 6. Okay. And we can look at all these things again in Desmos. So let's go check these out. Here's e to the x. The first order Taylor polynomial just is a horizontal line. Second order Taylor polynomial, so actually let me call this P0 of x. Or sorry, that's the 0th order. The first order is the tangent line, right? 1 plus x. There it is right there. Glorious. The second degree Taylor polynomial is 1 plus x squared over 2. That's sort of the best fit parabola to the function y equals e to the x at x equals 0. If I zoom really far in, you can see that this parabola really closely matches the shape of y equals e to the x, especially if I zoom in really far, right? So there you go. And by the way, I'll show you the remainders in a second too, but here's P3 of x. This is sort of the best fit cubic function to the function, to the curve y equals e to the x cubed over 6. There we go. And again, if I zoom in, you can see that this cubic function is really closely lining up with the function y equals e to the x at x equals 0. Okay, so there's sort of that family of tangent curves to the curve y equals e to the x. Now here are the remainders. Let me turn all these off. R0 of x is e to the x minus 1. There's that remainder. R1 of x is e to the x minus 1 minus x. There's that remainder. R2 of x is e to the x minus 1 minus x squared over 2. And the remainder R3 is e to the x minus 1 minus x squared over 2 minus x cubed over 6. And you can kind of see that as we look at higher order Taylor polynomials, the remainders get flatter and flatter near the center of the Taylor series. Okay, this third degree remainder is really, really, really flat at the center x equals 0. Okay. Which is important once we start talking about convergence and what does the Taylor series actually converge to. Pretty cool stuff. All right. So that's Taylor polynomials and the remainder. Everyone take a second, pause the video, and try this question out on your own. The numbers here are a little gross, but not terrible. Find P2 of x at a equals minus 1 for the function f of x equals square root of 5 plus x. And then what's the corresponding remainder? So take a second, pause the video, find the second degree Taylor polynomial centered at a equals 1 for this function. So again, and also, again, this subscript always tells you the highest power of x that you should potentially see. All right, so hopefully you paused the video. We know that P2 of x is going to be the sum n equals 0 to 2 of the nth derivative of f at minus 1 over in factorial times x minus minus 1 is x plus 1 to the n. Okay, so this is what we want to evaluate. So we need the 0th derivative of f at minus 1, the first derivative, and the second derivative. Okay, so the 0th derivative of f of minus 1 is simply f of minus 1, which is the square root of 5 minus 1, that's the square root of 4, which gives me 2. The first derivative of f at x is, well, by the chain rule, 1/2 times 5 plus x to the minus 1/2. And so f prime of minus 1 is, well, 1/2 times, when I plug in minus 1 for x, I get 4 to the minus 1/2. That's also 1/2, so I get 1/4 there. And lastly, f double prime of x looks like, well, 1/2 times minus 1/2 times 5 plus x to the minus 3/2 when you take another derivative. So f double prime of minus 1 is, well, minus 1/4 from that times 4 to the minus 3/2. That's like minus 1/4 times 1 over 4 to the 3/2. 4 to the 1/2 is 2, so that's like 1 over 2 to the third. So that's minus, what, 1 over 32? 4 times 8? Yeah, minus 1 over 32. So once I start writing this out, P2 of x is f of minus 1 is 2 plus f prime of minus 1 over 1 factorial, that gives me that 1/4, times x plus 1 to the first. And lastly, we've got f double prime of minus 1, that's minus 1 over 32, divided by 2 factorial times x plus 1 squared. And simplifying this, this is P2 of x equals 2 plus 1/4 x plus 1 minus 1 over 64. Let me scooch this a little bit. Oops, sorry everybody. Times x plus 1 squared. Leave it like that. Don't expand the square. Just leave it like this. It's perfectly fine to leave it that way. Okay. And the remainder, R2, come on, R2 of x just looks like square root of 5 plus x minus that 2 plus 1/4 x plus 1 minus 1 over 64 times x plus 1 squared. And if you want to distribute the negative, you can, but let's again go to Desmos and make sure that this matches up with the curve that we're looking at. Okay, so if I go into Desmos, get rid of this example, okay, and look at f of x is square root of 5 plus x. Zoom out a little bit. There we go. There's that function. P2 of x is 2 plus 1 over 4 times x plus 1. So there's the tangent line at x equals negative 1. You can see that they line up at x equals minus 1. And then minus 1 over 64 times x plus 1 squared. So there's sort of the best fit parabola, right? Oopsies, the tangent parabola. There we go. Lines up at x equals negative 1. And actually, Desmos is a little silly here. Desmos is having trouble with round-off error. But there you go. There's that second-degree Taylor polynomial. Okay. And here's the second-degree remainder, f of x minus p2 of x. Okay. Again, you can see how flat it is close to x equals negative 1. Very cool. All right. So let's look at another way to write that remainder term um, that just looks like Rn of x equals f of x minus the uh, nth degree Taylor polynomial, which looks like f of x minus the sum n equals 0 to, sorry, let me use k because I'm using an n there, of nth derivative, kth derivative, sorry, of f at a over k factorial x minus a to the k. Okay, so I don't think I have it written down here. Yeah, so this is called Taylor's theorem, and it says that another way you can write this remainder is as follows. There is a C between x and a such that Rn of x, which is equal to f of x minus Pn of x, is actually just equal to what you would get for the next term in the Taylor series. So write down what is the next term, the n plus first term. Well, that looks like f to the n plus 1 derivative, right? The n plus first derivative of f over n plus 1 factorial times x minus a to the n plus 1. And you'll notice I left the argument of the n plus first derivative empty. And that's because I need to incorporate the c that goes in the argument there. Okay, so there is some c between x and a such that the remainder term looks like that n plus first derivative. It just looks like the next step in the Taylor series, but instead of evaluating the function at a, you're evaluating it at some c. That in practice, we never know. That we never know in practice. Okay, so this is what's known as Taylor's theorem. It is incredibly important for doing things like error analysis in a class like numerical analysis, proving certain things converge to what we expect them to, and so on and so on. So this theorem, Taylor's theorem, is one of the most important theorems from Calc 1 and 2, honestly. Um, there is another way to write this that uses integration by parts that I really like. So this is Taylor's theorem with, I believe it's called Taylor's remainder. There's another way to write this with what's known as the integral remainder. So let's look at the integral remainder. And this is one of the only times that when I'm doing integration by parts that it's important to be able to add a constant with the dv part. Okay, so let's use the fundamental theorem of calculus to say that f of x minus a, sorry, f of x minus f of a, that's equal to the integral from a to x of f prime of x, sorry, of t. I need a dummy variable here with respect to t. Right? That's the fundamental theorem of calculus right there. Hopefully nothing controversial. And let me move things over. So this will become that I'm going to add f of a over, oops, plus, and then scooch this equals over there. Okay, so that's just a rearranged version of the fundamental theorem of calculus. Okay. And now let me start doing integration by parts. U, d, v. And I'm going to do the only thing that I can do. I'm going to put f prime of t as u and dv as just 1 dt, right? I'm going to start differentiating on the left. I get second derivative of f at t, and integrating on the right. I get t plus, I'm going to write the plus c for a second, and just see what we get. Plus minus. Okay. So this looks like f of a plus, when I evaluate using integration by parts, what do I get here? I get t plus c times f prime of t evaluated at x, or sorry, t equals x, and t equals a. And then minus the integral from a to x of f double prime of t times, scooch this over a tiny bit, times t plus c dt. And I'm going to pick c so that I get the first degree Taylor polynomial on the right hand side. Let's see how we do that. This is f of a plus, when I plug in x for t, I get x plus c times f prime of x, minus, when I plug in a for t, I get a plus c times f prime of a. Okay. And then minus that stuff. So I want to end up getting the Taylor polynomial, the first degree Taylor polynomial out of this. And I have the freedom to pick c. The integral is with respect to t. So x and a are kind of being treated like constants. So notice this part looks like the Taylor polynomial going on. This part doesn't because I've got an f prime of x and not an f prime of a. Okay, so I want to keep this part around, and I kind of want to get rid of this part. So I'm going to choose c equals negative x to get rid of this part right here. If c is negative x, then that's 0. And let's see what we get. We end up with f of a plus, well, that second term goes away by design, a minus, or sorry, that should be a minus a minus x times f prime of a minus the integral from a to x of f double prime of t times a, or sorry, t minus x, right? dt. And now let's distribute some negatives. This looks like f of a plus x minus a, f prime of a, and then plus the integral from a to, well, actually, we can just leave it as, let me replace c with minus x. And I'm just going to leave that in that form. So minus the integral from a to x of f double prime of t times t minus x dt. Okay. And so notice we've got a remainder term here, right? I have f of x is exactly equal to this stuff. So now this is known as the integral form of the remainder, and you can actually play some games with this to make this even more easy to evaluate. But you can also use this as what's known as the integral remainder. Okay, and there's no reason to stop at the first derivative. I could have come over here and done another derivative, and over here, if I integrate t minus x with respect to t, I get t minus x squared over 2, right? And then this becomes a minus, and then like this becomes a plus. And so we also get that this looks like, well, f of a plus t minus x times f prime of t minus t minus x squared over 2 times f double prime of t, all evaluated at t equals x and t equals a, and then plus the integral from a to x of f triple prime of t times t minus x squared, sorry, divided by 2 dt. Right? And when you actually evaluate that, you end up with f of a plus x minus a f prime of a plus x minus a squared over 2 times f. Uh, why am I writing it in that silly way? Let me write this as f double prime of a times over 2 times x minus a squared, and then plus this integral remainder. Okay. And you can keep going. In general, and so this looks like, so this is, again, f of x equals p2 of x plus r2 of x, right? And in general, you can also write the remainder, r capital N of x, as the integral from a to x of the n plus first derivative of f at t times t minus x to the capital N over n factorial dt. And again, if you can use the mean value theorem for integrals to actually write this a little simpler. But most of the time in practice, this is the version that you work with, just so you know. Okay, so that's that. And also, you can kind of use this integral form to get to this um, the Taylor's form of the remainder. So that's it for Taylor series. So that'll be a very fun set of lecture slides. So thank you all for watching this. Feel free to email me if you have any questions, and I'll see you guys. Well, you'll see me in the next video. Thank you. Have a great rest of the day.